Hi students, welcome back once again. Chapter 7, Rotational Dynamics, quick revision. We start with different types of rigid body motion. The first one is pure translation. In pure translation, each of the particles of that rigid body moves with same velocity, and velocity of center of mass of that rigid body is same as that of each of those particles. Example, sliding. A box is sliding. So all particles will have same velocity. And that is translation. Velocity of center of mass is equal to velocity of each of those particles. Second type is pure rotation. Pure rotation. Fixed axis rotation or pure rotation. In pure rotation, we use the formula V is equal to R omega. V equals R omega. In pure rotation, a particle can rotate about a fixed axis at a constant radius R and angular speed omega. If that particle is P, which is undergoing a circular motion in horizontal plane with a radius R, at an instant its speed is V, then that speed can be measured by V equal to R omega. And this type of motion, fixed axis rotation, there is only rotation, no translation. Center of mass will not have any translation. So that particle has a rotational kinetic energy. Center of mass has no translation, so particle has a rotational kinetic energy. The particle is acted upon by a torque, net torque. If there is a net torque, there will be an angular acceleration. Angular acceleration alpha is equal to d omega by dt. If angular speed increases, the linear speed also increases. Then alpha is positive. If omega decreases, if alpha is negative, like this, that may be non-uniform circular motion, but still it is fixed axis rotation. So fixed axis rotation can have particle moving with equal speed or variable speed, both possible. That is fixed axis rotation. Second type, pure rotation. Now the third type is rolling. Rolling is the combination of translation and rotation. Rolling is the one which is most prime here. Rolling. When a body rolls on a surface, the center of mass of that rolling body has got a velocity V, C, where C stands for center of mass. Vc is the velocity of center of mass. Every particles of that rigid body moves with same velocity. In addition to that, the particles other than that and other than its center of mass possesses rotation also. So all particles will have translation and rotation except at center of mass. The particle at center of mass only has translation. All the other particles will have translation as well as rotation. That is called rolling. We have in our syllabus only pure rolling. That means rolling without slipping. If this body is rolling without slipping, a particle at radial distance r, then the speed of that particle at radial distance r will be r omega with respect to center and 2r omega with respect to the bottom. So speed of the topmost point will be 2r omega with respect to bottom, so that speed of the bottommost point is 0. Speed of center of mass is Vc. Speed of topmost point is 2Vc. That is equal to 2Vc or Vc equal to R omega. Such a rolling is called pure rolling, where the particle at the periphery, when makes one complete rotation, the center of mass translates through a distance Vc equal to R omega, which is equal to 2 pi r. The distance traveled by the center of mass for that peripheral particle completes one rotation is equal to 2 pi r. So distance traveled by the center of mass for one full complete rotation, that is equal to 2 pi r. Similarly, velocity of center of mass is equal to r omega if center of mass has an acceleration, if center of mass is acted upon by net force. Once again, derivative acceleration of center of mass is equal to r alpha. So these are the conditions for pure rolling or rolling without slipping. Vc equal to r omega, Ac equal to r alpha, Sc equal to 2 pi r. The displacement of the center of mass is 2 pi r for one full rotation. Okay. At that time, the distance traveled by any particle at the periphery will be 8 times the radius, 8r. You can keep it as a knowledgeable answer. Distance traveled by the peripheral particle. That particle will move in a complex path called cycloidal path, cycloid. The peripheral particle moves in a cycloidal path, cycloid. But center of mass follows a linear path. Center of mass goes in a straight line. Peripheral particle goes in cycloid path. Distance moved by particle at the periphery for one full rotation is 8 times the radius. But displacement of the center of mass when the particle defines one circle is 2 pi r. That's the difference. That's pure rolling. During pure rolling, bottommost point remains at rest. Topmost point has a velocity 2 times velocity of center of mass. So the middle of center and top, suppose this distance is r by 2. Its speed will be central value of r omega and 2r omega. That is what? 3 by 2 r omega. And this part, if this distance is r by 2, this velocity will be r omega by 2. So the speed of the particle at the bottom with respect to the bottommost point is 0. Speed of center of mass with respect to bottommost point is r omega. Speed of topmost point with respect to center of bottommost point is 2r omega. So the fastest one is at the topmost point. When that particle reaches the top, it becomes faster. Then its speed reduces, becomes 0. Then increases, becomes maximum. Like that. All dealt in terms of the axis passing through the bottommost point, called instantaneous axis of rotation. That's all about pure rolling. More things, acceleration, inclined plane related questions will be discussed later. These are the 3 types of rigid body motion. One more type is there, that is called precession. Fourth one is precession. Spinning top is an example of precessional motion. In precessional motion, there are 2 axes. A rigid body rotates as well as revolutes. A rigid body spins about its own axis. And also the same rigid body rotates or oscillates about another axis together with this spinning. So 2 angular speeds are there simultaneously. One is angular speed due to spinning. Other one is angular speed due to precessional motion. Spinning top is an example of precessional motion. The spinning effect of precessional effect of the spinning top can be seen at the end of a spinning top. When it performs that, it is an art. You try to watch the spinning wheel or spinning spin. It will rotate and revolute. At the last stage, just before it falls down, that is called precessional motion. There, the bottommost point is fixed, and and that fixed point will be the point of intersection of two axes. There are two axes. Spinning top has two axes. One is vertical, other is inclined. And the point of intersection of two axes is fixed. And about one axis, other axis precesses. That is called precessional motion. These are the four different types of rigid body motion. Now we begin center of mass. What do you mean by center of mass? Center of mass is an imaginary point at which entire mass of a rigid body is supposed to be concentrated. While learning rigid body dynamics, it is very important to learn about center of mass. Center of mass is defined as in Cartesian coordinate system. Position vector of center of mass is equal to m1 r1 plus m2 r2 divided by m1 plus m2. In one particular type of frame of reference called center of mass frame of reference, C frame, definition is still more easy. In center of mass frame of reference, center of mass of that rigid body is attached with the center of mass of the rigid body is attached with the origin of the coordinate system. Are you following? Center of mass of the rigid body is attached with the origin of the coordinate system. That is why the position vector of center of mass will be 0. That is why the velocity of center of mass will be 0. That is why the momentum of center of mass will be 0, so called zero momentum frame. C frame is also called zero momentum frame. Then we can also write m1 r1 is equal to minus m2 r2. So this concept is very much used in many situations. For example, if a person is moving on a platform is on a frictionless surface. When the person is walking on that rough platform, that platform itself is placed on a frictionless surface. When the person walks on the platform itself moves back. In such situations, what is the resultant displacement of the platform or man, whatever is asked? You can use this C frame concept, m1 r1 equal to minus m2 r2. Also, you can use this principle to find the center of mass of a rigid body after removing a small amount of symmetric mass from it. For example, a disk of mass m and radius r. Another small disk of radius r by 2 removed from one end. Then where the new center of mass is located. All that we can use m1 r1 equal to minus m2 r2. During radioactive decay, one example is mentioned here in our textbook. Radioactive decay. Radium decays into radon and alpha particle. Radium, which is highly radioactively unstable, goes radioactive disintegrations and it becomes radon as well as an alpha particle. It is here. Radium disintegrates into radon and alpha particle. Alpha particle is helium nucleus. Then also you can use this principle. If M1 is the mass of helium, M2 is the mass of radon, R1 is the distance of helium from radon, parent radon, M2 is the distance of radon from radium, helium from radium R1, radon from helium R2, we can use M1R1 equal to minus M2R2. That is why they are moving in opposite direction to conserve momentum. M1R1 equal to minus M2R2. The lighter one is helium has moved far apart. Heavier one, radon, has moved only very little. So we can locate the position of center of mass of two particle system very easily. Center of mass of two particle system will be close to the heavier mass. This idea is used a lot in competitive examinations. Here another example of center of mass. Here radium is moving initially with constant speed. During when radium is moving, it undergoes decay into radon and helium. Now the center of mass is moving with constant velocity after decay process. But in the next case, radium was at rest. After decay process, helium and radon will move in such a way that the center of mass of radium is at rest after the process also. Before the process it was at rest. It is because this process there is no external force. It is radioactivity, nuclear radioactivity. The nuclear process. In that process, there is no external force. In the absence of external force, total linear momentum is to be conserved. For that, before that process, momentum of center of mass was zero. In the second case, after the process also momentum of center of mass should be zero. In the absence of external force, momentum of center of mass does not change. Before it was zero, now also it is zero. But in first case, before the process also center of mass was moving with constant velocity. After this process also center of mass would be moving with constant velocity. One more example can be mentioned here. Here is the case of binary stars. Binary stars are two stars which are having nearly equal masses, not exactly equal, nearly equal masses, comparable masses, which are revolving among themselves under mutual gravitational attraction. Mutual gravitational attraction. As the stars are having different masses, these two stars will undergo different circles of different radii, but with same center. So each of those stars in binary stars will move in concentric circles with different radii. Always each of that stars will be at the diametrically opposite points. And the heavier star will be close to center of mass. So radius of the heavier star executing circular motion will be less. Radius of the lighter star executing circular motion is more. So lighter one describes more radius. M1R1 equal to M2R2. M proportional 1 by R. Mass കൂടിയതിന് radius കുറവാണ്. And അതാണ് C prime advantage. Okay. While learning center of mass, it's very important to learn about these binary stars. Here, first picture, trajectories of two stars S1 and S2 forming binary system. Their center of mass is in uniform motion. So when you see from an external or laboratory frame, you will notice center of mass moving with constant velocity in a straight line. But when you notice the stars will move in a complex path like a helical path. Each of that helical spirals, stars will be at the diametrically opposite phases. Like this only they will be moving. So that total path seen from outside, if you notice, stars alone is helical. Center of mass follows a straight line. Stars follow helical path from a laboratory frame. But when you look it from center of mass frame, you are going into the center of mass. You are at the center of mass of the stars. And you are watching that stars. One star is above, then the other star is below. And you, that means center of mass. S1 and S2 all will be in same line. So very difficult, very easy to analyze. Then you see the path of that starts to be circle, not helix. Circle is much easier than helix. Helix is 3-dimensional, circle is 2-dimensional. So C frame helped you in reducing the number of variables. Number of variables used for describing the trajectory of the particles. That's the advantage of C frame. Another one you can see here, it's a firecrack. Firecrack. Firecrack normally, if it was not exploded, it would have been gone in a parabolic path in the absence of explosion. But on the way, in midair, it explodes into fragments. But that explosion is only creating an internal force. Internal force cannot make any change in the trajectory or state of center of mass. With respect to center of mass, that exploding force is an external force. That's why the center of mass will follow a parabolic trajectory even after explosion. The fragments will be moving in such a manner that that explosion will not affect center of mass. Center of mass will not know that this explosion has happened. Center of mass will not know that explosion has happened. That's why center of mass would follow the same path as if it were not exploded. അപ്പോൾ പൊട്ടാത്ത പടക്കം, ചീറ്റിപ്പോയ പടക്കം ഏത് വഴിയിലൂടെ പോയിരുന്നേനെയോ ആ വഴിയിലൂടെ തന്നെയാണ് center of mass പോകുക. Okay, because path of center of mass of fragments will be complex, but path of center of mass is so simple, it will still follow parabolic path. Similarly, if a firecrack is dropped from rest, on the way, if it explodes into fragments, then also center of mass will go in same straight line path, because center of mass was following a linear path before. Now also comfortably, it does not know that explosion has happened. That's the thing. So what is the conclusion? In the absence of external force, center of mass does not change its state. That's very important. That's important, and we can also discuss the formula for velocity of center of mass. Velocity of center of mass is that m1 v1 plus m2 v2 by m1 plus m2, all that applied anywhere. Acceleration of center of mass, m1 a1 plus m2 a2 by m1 plus m2. But force on center of mass is not m1 f1 plus m2, it is only f1 plus f2. Momentum of center of mass, p1 plus p2. But velocity of center of mass, v1 plus v2 is incorrect, m1 v1 plus m2 v2 by m1 plus m2. Position vector of center of mass, m1 r1 plus m2 r2 by m1 plus m2. So this force and momenta are additive regarding center of mass. Force on center of mass is sum of forces on each of the constituent particles. I mean vector sum. That's the thing, and that is very important, and I told you the applications where it comes also. Together with, we have already discussed many important concepts. Conservation of momentum of center of mass also can be discussed here. F is equal to dp by dt. If F represents net external force acting on center of mass and P represents total linear momentum of center of mass. If external force is zero, total linear momentum is a constant. That's why center of mass does not change its state. Binary stars, alpha decay, all this we have explained. Now vector product of two vectors A and B can be multiplied by the method of vector product, which is A cross B, is defined as AB sin theta. So vectors A cross B is equal to A B sin theta n cap. In this chapter, we have used so many vector products. One among them is relation between V, omega and R. V equal to omega cross R. Another one is A is equal to omega cross V. That is centripetal acceleration. Another one is tangential acceleration alpha cross R. Another one, angular momentum L is equal to R cross P. The next one is torque tau is equal to R cross F. All this vector product we employ here. Cross product of two vectors is also a vector. The plane in which cross product appears is in a plane perpendicular to the component vectors. Suppose, for example, R and P are in XY plane. So L is along Z axis. That may be in positive or negative Z axis. So any one of this can be practiced now. Let us do the practice of torque vector. We make use of the Cartesian coordinate system. Origin is O. Now position vector is R. One of the forces is F1, but other force is F2. And R cross F1 is equal to tau 1. And let the other force be F2. Then R cross F2 equal to tau 2. This is the way by which we practice it. So applying right hand screw rule. See my fingers I am holding how. R cross F1. Hold from right hand fingers from R to F1. R to F1 you turn like this. Then thumb will point inward. So F1 has a torque tau 1 along negative Z axis. So tau 1 is tau 1 minus K cap. Similarly, the force F2 produces a torque in positive Z axis. So it should be expressed as plus tau 2 K cap. So that is the way by which we apply cross product rule. Cross product is perpendicular to the component vectors. Orthogonal unit vectors have also an important cross product. I cross I cap cross I cap is equal to 0, J cap cross J cap 0, K cap cross K cap 0, but I cap cross J cap is equal to K cap. For that, knowing that you use I, J, K curve, I, J, K cycle. For example, I cross J equals K, J cross K equals I, K cross I equal to J. But reverse, everything will be minus. For example, J cross I is minus K, I cross K is minus J, K cross J is minus I. So I cross J equal to K, J cross K equal to I, and K cross I equal to J. So this is the way by which we get the cross product of two vectors. So we have many applications of cross product in this chapter. Other application is angular momentum. Let us see an example in our textbook. In our textbook, an object is moving with velocity v parallel to positive direction of x-axis. An object of mass m moving with velocity v parallel to positive direction of x-axis. If we examine that from this point O, that object seemingly turns around O. Even when that object itself moves in a straight line, in its own frame it moves in a straight line, but from an external frame which is at a perpendicular distance r sin theta, seems to be turning around O. So there is a turning effect of linear momentum about O, so it possesses angular momentum. So L is equal to R cross P. What is the direction of that angular momentum? Position vector is R, momentum vector is P, R cross P is directed along negative Z axis. So that angular momentum vector constantly acting along negative Z axis. Let us check whether its magnitude is constant or not. We know as the time progresses, R increases. As R increases, we may think that value of L also increases, but it is incorrect because it can be measured as M, V, R sin theta numerically. Here r sin theta is a constant. R sin theta is the perpendicular distance between O and M. That is a constant. That is why when r increases, value of theta decreases. R increases later on and later on r increases, theta decreases, so that r sin theta is kept a constant. That's why angular momentum vector is a constant in its magnitude as well as direction. So angular momentum vector is a constant in magnitude and direction. Okay. Another application. A body is rolling case we have already discussed. An object is moving by rolling without slipping. Rolling without slipping. Now the center of mass has got a velocity v, its mass is m. About this bottommost point O, that object has got an angular momentum. What is the angular momentum of that rolling body? Angular momentum of center of mass. Angular momentum of center of mass of the body, or angular momentum of the body itself, means angular momentum of its center of mass, equal to momentum into perpendicular distance. Momentum is mv, perpendicular distance is r, so mvr is its angular momentum. Like this, there are several applications while finding angular momentum. Also, you can apply Newton's law here, connecting torque and angular momentum. As per Newton's law, we have learned the equation tau equal to dl by dt, where tau is the net external torque. Also, if external torque is 0, L is a constant in both magnitude and direction. That is angular momentum conservation rule. So all these equations finds importance and significance in this chapter. Now we will move on to revision of moment of inertia. Moment of inertia is going to be an important topic here. Moment of inertia is also called rotational mass or rotational inertia. Moment of inertia of a particle of mass m, which is situated at a distance r from an axis, and this is the axis. Moment of inertia of that particle about that axis is defined as the product of mass and square of the perpendicular distance. If it is a particle, it's easy to define the moment of inertia of a particle, but moment of inertia of a rigid body is very difficult, for which we need to know the radius of gyration of the rigid body. Radius of gyration of the rigid body is the distance of that center of mass, distance at which a particle of same mass, which when placed gives same moment of inertia. Rigid body moment of inertia എന്താണ് എന്ന് നമുക്ക് ആദ്യമേ അറിയണം. അതേ moment of inertia കിട്ടുന്നതിന് വേണ്ടി ആ റിജിഡ് ബോഡി ഏത് ഷേപ്പ് ആണെങ്കിലും അതിനെ കൊണ്ട് ഒരു പാർട്ടിക്കിളിനെ ഉണ്ടാക്കി ആ റിജിഡ് ബോഡിയുടെ ആക്സിസ് ഏത് ആക്സിസിനനുസരിച്ചാണോ നമുക്ക് അതിന്റെ മൊമെന്റ് ഓഫ് ഇനേഷ്യ അറിയാവുന്നത്, ആ ആക്സിസിൽ നിന്നും എത്ര ദൂരത്തിൽ വെക്കുമ്പോഴാണോ ആ പാർട്ടിക്കിളിനെ എത്ര ദൂരത്തിൽ വെക്കുമ്പോഴാണോ അതേ മൊമെന്റ് ഓഫ് ഇനേഷ്യ കിട്ടുന്നത്, നമുക്കറിയാവുന്ന മൊമെന്റ് ഓഫ് ഇനേഷ്യ കിട്ടുന്നത്, ആ ദൂരത്തെ വിളിക്കുന്ന പേരാണ് റേഡിയസ് ഓഫ് ഗൈറേഷൻ. ഓക്കെ, the general equation for moment of inertia therefore leads to mass of the center of mass, mass of the rigid body, into k square, where k is the radius of gyration. What is the radius of gyration of a thin uniform ring? What is the radius of gyration of a thin uniform ring about the axis of rotation? We know moment of inertia of a thin uniform ring about the axis passing through the center of mass and perpendicular to its plane is mass m, radius r, m(r) square. Then what is the radius of gyration? You equate that to m(r) square. So m gets cancelled, you get k is equal to r. Similarly, for a disk, thin uniform disk for same axis, radius of gyration would be mk square equal to m(r) square by 2. That is k equal to r by root 2. K equal to, it should be r by root 2. Okay. For a solid sphere, What is moment of inertia of a solid sphere? I equal to 2 by 5 mr square. So radius of gyration will be what? Mk square is equal to 2 by 5 mr square. Strike out m. So k is equal to root of 2 by 5 into r. So that root of 2 by 5 is the coefficient. Take root of that. What about a hollow sphere? Hollow sphere. Hollow sphere or spherical shell. K equal to root of 2 by 3r. Like this, radius of gyration, that part is important. Radius of gyration also changes with the position of axis and orientation of axis. Moment of inertia depends on mass of the body, distribution of mass of the body, position of axis, orientation of axis, size, shape, radius of gyration, everything. It depends. Moment of inertia does not depend on angular speed. Moment of inertia does not depend on angular speed. It is also called rotational inertia, rotational mass. There are two important theorems based on this, parallel axis as well as perpendicular axis theorem. Let us revise that more. You have a thin uniform ring. Moment of inertia about an axis passing through the diameter of the thin uniform ring. We know about the diametrical axis of thin uniform ring of mass m and radius r is m r square by 2. Then what is the moment of inertia about an axis passing through the tangent and parallel to the plane? Moment of inertia of the diametrical axis mr square by 2. So about this axis, new moment of inertia is moment of inertia about an axis passing through center of mass plus mass of the center of mass into square of that distance. Here that distance is r. That is why I is equal to moment of inertia about axis passing through center of mass is mr square by 2 plus mass of center of mass is m into d square is r square. That is why mr square by 2 plus mr square, that implies 3 by 2 mr square. And this is one of the applications. Based on that, let me revise. Moment of inertia of thin uniform ring about an axis passing through center of mass and perpendicular to the plane of the ring is mr square. Now move that axis from center to end. That is the tangential axis. Is it clear from this? Okay, as it is a part of quick revision, I do not have that much of time to show in the board. So this is mr square. This will be 2 mr square. Just you move from center to end, you add mr square simply. Here also the same. Mr square by 2 plus mr square is 3 by 2 mr square. Like that. So thin uniform ring, mr square, 2 mr square, then mr square by 2 and 3 by 2 mr square. What about it if a thin uniform disk? Thin uniform disk moment of inertia about center of mass, mr square by 2, about tangential 3 by 2 mr square, 3 by 2 mr square. If it is disk, it is written for ring, right? It is disk mr square by 2, 3 by 2 mr square. And for disk it is mr square by 4 and this is 5 by 4 mr square. For solid sphere, center of mass 2 by 5 mr square, tangential axis 7 by 5 mr square. Hollow sphere, center of mass 2 by 3 mr square, tangential 2 by 3 plus 1, 5 by 3 mr square. Like this. Center of mass, moment of inertia of a thin uniform rod about center, ml square by 12, about 1 end, ml square by 3. All these are very important. So moment of inertia and simple applications based on parallel axis theorem and perpendicular axis theorem. How to apply perpendicular axis theorem? While applying perpendicular axis theorem, if you have the coordinate system and a ring is kept like this, and this axis is y axis, and this axis is the x axis, one more axis, another color, that is z axis. Then the ring is kept in xz plane, the thin uniform ring kept in xz plane, and this is y axis. If the ring is kept in XZ plane, you can add moment of inertia of the ring about x-axis and z-axis to get that y-axis. So as the ring is in XZ plane, Iy is equal to moment of inertia about the perpendicular axis is equal to sum of moment of inertia about the other two axes. Okay, but y should be perpendicular to x, y should be perpendicular to z, y should be perpendicular to z, but x and z need not be perpendicular. Then also we can apply this. But if here x and z are perpendicular. Okay, this is perpendicular axis theorem. So these two theorems use also, simple uses are also important. Now the last topic of the chapter is rolling. Rolling. When a body is rolling, the total energy of the rolling body is the sum of translational and rotational energies. So total energy of rolling E, kinetic energy, is equal to kinetic energy of rolling plus kinetic energy of transit, rotation plus kinetic energy of translation. Kinetic energy of rotation is half I omega square. Kinetic energy of translation is half m v square. Okay, this is the total kinetic energy of a rolling body. General formula, we do not know the shape of the body. Then you can write I as mk square, omega as v by r and omega square, v square by r square. Then we write half m v square into 1 plus k square by r square, where this k square by r square is equal to beta. Let us choose that as beta a constant. So total energy of a rolling body is half mv square into 1 plus beta. So what is total energy? Total energy is the sum of kinetic and potential. Kinetic, translational kinetic and rotational, both. E equal to half mv square into 1 plus k square by r square. This formula can be used as an important one. Now, if you have an inclined plane, a body is rolling down, the shape you do not know, rolling without slipping. What is that acceleration if the inclination is theta? So acceleration of the rolling body equal to g sine theta divided by 1 plus beta. If it was sliding without rolling, it would have been g sine theta on a frictionless surface. On a frictionless incline, the acceleration would have been g sine theta. But if it is sufficiently rough enough to permit rolling without slipping, acceleration would have been g sine theta by 1 plus beta. When it reaches down to the bottom, its velocity, when it reaches down to the bottom from height h, the velocity gained by it, if it is sliding without friction, no friction there anywhere, and it is sliding, not rolling, then V is equal to root of 2g sine theta into L, where L is the length, root of 2g sine theta into L. Okay, but as it is rolling down, it should not be this. As it is rolling down, what should be this? Root of 2 into A. A is g sine theta by 1 plus beta into that distance, root of 2 A. Yes, S means that L. So root of 2 g sine theta by 1 plus beta into L, root of 2 A L, where A is the acceleration down the inclined plane and L is the length of inclined plane. You can also use sine theta as h by L. Sine theta as h by L. So that you can also write V equal to root of this sine theta can be written as h by L, or L sine theta can be written as h. So simplify this, root of 2gh by 1 plus beta can also be used. So in terms of h and L, practice this. So acceleration and velocity. So what is the time taken by the body to roll down? Time taken by the body to roll down is equal to time is equal to root of 2 into L is the length over which it comes down. Root of 2L divided by A. A is G sine theta by 1 plus beta. Here also you can use sine theta is equal to H by L. Sine theta equal to H by L. Sine theta equal to H by L as in the previous slide. So that L can be written as H by sine theta. So that time can be written as root of 2h into 1 plus beta divided by G sine square theta. So we have substituted L as H by sine theta. Put L is equal to H by sine theta. So root of 2h into 1 plus beta by G sine square theta. So these two equations are also worth noted. So what is the time after which a body rolls down an inclined plane? What is the time after which a body slides down an inclined plane? Differentiating, all this important. While sliding, you need not use this beta and that term. Only the time will be root of 2L by G sine theta. Okay. So total kinetic energy of a rolling body, velocity of a rolling body down an inclined plane, acceleration of rolling body, all this are very important topics of this chapter. The last content of the chapter is regarding conservation of angular momentum. Conservation of angular momentum. In the absence of external torque, total angular momentum is a constant. Tau external equal to 0, so L is equal to a constant. We have already learned the formula for angular momentum as moment of inertia times angular velocity. So that is a constant. Then we can use I1 omega 1 equal to I2 omega 2. In the absence of external torque, angular momentum is a constant. So I1 omega 1 equal to I2 omega 2. There are many questions based on this. A child turning in a round table quickly without any external agency, he outstretches the arms. Moment of inertia increases due to increased distribution of the mass. Angular speed automatically reduces. A child can adjust the speed of rotation by stretching or folding the arms without any external aid. A springboard diver exploits this. A springboard diver can change the rotational speed in air after jumping from the springboard by folding his body inward or distributing outward. While folding inward, angular speed increases. By spreading his body outward, angular speed decreases. A cat falls down from whatever height in right position with all its 4 legs touching ground, for which it adjusts itself, its body. The cat has never attended any physics classes, but it knows how to manage for its safety. A safe landing, it will turn around so that it touches ground in its 4 feet. Due to global warming, due to melting of ice in polar regions, the more amount of water flows, the rate of melting of ice is increased due to rotational effect of Earth. That water rushes towards the equatorial region. Even when the mass remains constant, the moment of inertia of Earth increases due to the increased amount of water from polar region onto equatorial region, due to which moment of inertia increases, and this happens without any external torque. That's why angular momentum is to be conserved. Then when moment of inertia increases, angular speed of Earth automatically reduces. When angular speed reduces, time period increases. When time period increases, time taken for once to rotate increases. When time taken for Earth to rotate once increases, length of the day increases. That's a natural consequence of this conservation of angular momentum. Many applications. Okay, this chapter is very important. Major concept of the chapter is rolling for entrance examinations as well as moment of inertia, torque, angular velocity. In addition to all this, you don't forget to revise the rotational kinematic equations. Rotational kinematic equations are omega equal to omega 0 plus alpha t. Theta is equal to theta 0 plus omega 0 plus t plus half alpha t square. And the third one is omega square minus omega 0 square is equal to 2 alpha theta. All these rotational kinematic equations used for constant angular accelerations. Okay, all this makes this chapter lengthy and also more important for all competitive examinations. You can expect 2 questions or sometimes 3 questions for Neet and mains 2 questions from single paper itself. You can expect 2 questions or sometimes 1. Neet paper you can definitely have 2 questions at least. Okay, then we have completed the quick revision of chapter 7, rotational dynamics. We will be meeting with the next chapter, gravitation, soon. Thank you.